Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the course on computer aided drug design. We will continue on the topic of force fields or molecular mechanics. This is going to be a very important topic, as I mentioned, so we have to spend a lot of time on this. Now these empirical force fields, each atomic number is divided into atom types, okay, based on the bonding and environment. For example, carbon can be many types: sp3 carbon, sp2 carbon, sp carbon, aromatic carbon, carbonyl carbon, okay, then cyclopropane type of carbon, cyclopropene type of carbon, so on actually, okay. And then parameters are assigned based on the atom types, okay. So each of these carbon may have a different carbon-carbon bond length, okay, and the constant where we use that also will change depending upon its sp3 or sp2 and so on. So we will look at some of those examples. There are different types of force fields depending upon what type of parameters they choose, what type of equations they choose, okay. Like one family MM2, MM3, MM4, these are molecular mechanics force field for small molecules. These are very good. MM2 or MM3 is good enough for small molecules if you are looking at drugs, okay. CHARM, this is chemistry at Harvard, macromolecular mechanics, this is another force field. AMBER, assisted model building with energy refinement. OPLS, optimized parameters for liquid simulation. CFF, consistent force field, so this is also used nowadays quite a lot. CVFF, valence consistent force field. Then MMFF, Merck molecular force field 94, then UFF, universal force field. These are just few examples, but there are many types of force fields which are there, and generally I think MM2, the CVFF, they are quite used very commonly, and of course CHARM and AMBER is also used quite commonly. Okay, so these force fields like MM2, MM3, AMBER, Sybil, UFF, MMFF, etc., they differ in the functional forms, what type of terms are used for bond stretching or angle bending and so on, okay, and the parameter values will change. So the functional forms may be differing from one force field to another, and the parameters may be differing from one field. Do not mix and match, this is very important. So if I use one, say MM3, I will do all my calculations for all the set of molecules with MM3. I will not mix and match because each set of force fields is internally self consistent, so remember that. Like I said, the functional forms between force fields may differ, the parameter values may differ. So if I use for some molecules MM3 and some molecules I use AMBER, I will get different answers, it is completely wrong. Some force field use united atoms, that means what do they do this? They condense hydrogen H with the heavy atoms to reduce the total number of atoms, but there is some reduction in accuracy. So instead of putting H separately, carbon separately, they may have a united atom which may condense H into the C, and they may have parameters. So but little bit of inaccuracy, but the number of calculations reduce dramatically, okay. So for example, if I take MM2, let us take MM2, look at the different types of carbons MM2 has, okay, different types of carbons. sp3 carbon, sp2 carbon in alkene, sp2 carbon in carbonyl imine, sp carbon, cyclopropane carbon, radical carbon, carbocation, sp2 carbon cyclopropene, sp2 carbon in aromatic, sp3 carbon in cyclobutane. So each of these carbon differs, so you may have different force constants, you may have different R0 values, and similarly look at this nitrogen, so many types of nitrogen, okay, so many types of nitrogen. sp3 nitrogen, sp2 nitrogen, amide type of nitrogen, sp nitrogen, pyridine, ammonium, okay, then pyrrole, azoxo, N double bond N, and so on, okay, nitro, NO2, imine, and And similarly oxygen, so many types of oxygen, sp3 oxygen, oxygen carbonyl, oxygen furan, oxygen carboxylate, epoxy, amine oxide, ketonium oxygen. So many different types of. So MM2 has large database for so many types of carbons, nitrogens, oxygens, hydrogens, sulfur, chlorine, bromine and so on, including even metals as you can see here. Okay, so if you have cobalt or nickel or iron or magnesium, selenium, tin, okay, so you are okay because MM2 has parameters for these. So calculations for all these energy can be done properly. But if you have some other metal, obviously it cannot handle, you may have to go for some other force field which can handle that particular metal, like for example, okay, platinum maybe, that is not in this list, okay, only some of them. Sometimes some softwares will assume some other similar group metal and replace it with what they have. So each of these force fields will have a different set of atom types, so different parameter values. So it is always good to use only one force field for all your calculation. For example, let us look at this sp3 carbon, sp3 carbon. So the L0, that is R0 which we use there can be 1.523, whereas sp3 sp2 it becomes 1.497, and similarly the force constant also changes quite a lot depending upon the type of carbon, right, sp3 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 sp2 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 sp2o, that is carbonyl, sp3 n sp3 and so on actually, okay. And similarly if for angle bending you have theta minus theta naught, so we can have different theta naught values and different constant values here depending upon, say for example, carbon 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 in sp3, carbon carbon in sp3 with hydrogen H, you get some other number here in force constant and so on actually, okay. So you see sp3 sp2 sp3 carbon, the theta naught varies, whereas sp3 sp3 tetrahedral 109, okay. So these numbers will change, these numbers will change depending upon the atom type and the environment. So remember, so like that the database for any force field will be stored. So when you draw a structure and you mention these are the different types of carbons, these are different types of oxygens I have, automatically these numbers will be selected. So the bond stretching energy, bond bending energy, torsion energy, non-bonded interactions will be calculated and the total energy of the molecule will be estimated. This is how these molecular mechanics force field approaches. So the more number of atom types I have, it will try to cover as much as possible in the overall space, okay. So that means your database becomes large, so they will get these values, you know, either from experimental reported in literature or through ab initio reported in literature, okay. Okay. So what is average error in heat of formation? When you calculate heat of formation using MM2, the average error in heat of formation may vary like this, okay. So as you can see, hydrocarbons are reasonably good, whereas when you go to aromatic systems, amines, it can be quite large, okay. So the errors, depending upon how accurate you want your calculations to be, you can decide on what you want to do, okay. So there are many force fields, like I said. MM2, this is developed by Norman Allinger, mainly for hydrocarbons, small organic molecules, has a large set of parameters, like I showed you in that table, large set of parameters that is continuously refined and updated for many different classes of organic compounds. So MM2, MM3, MM3 plus, MM4 and so on. So this is a very good force field if you are looking at drugs, organic molecules, okay, without any metals or something. Then of course CFF, okay, this is developed by these people, is a general method for unifying studies of energy, structures, vibrations of general molecules and molecular crystals. The program was developed by these two, is based on the Cartesian representation of all the atoms, okay. And then based on the CFF, many other force field of this family consistent came into, I will show some of them, okay. So more of them, assisted model building and energy refinement, this is called AMBER force field. This is widely used for proteins. So, you see if you have a lot of protein, we can use this. Then comes CHARM. CHARM is another very popular force field used for small molecules and macromolecules. So, generally type of force fields are used for organic drugs, AMBER is used for proteins, CHARM is used for small molecules and macromolecules. This is the rule of thumb. So, you can use type of force fields, you can use AMBER or CHARM, okay, depending upon whether it is small molecule drugs, macromolecules, or whether it is a protein. CVFF is broadly used for small molecules and macromolecules. Yes, some softwares use that, CVFF, that is a consistent valence force field. This is Cosmos NR, it is a hybrid of quantum mechanics and molecular mechanics. So, it combines little bit, adds little bit of quantum mechanics adapted to a variety of inorganic compounds. Okay. So, if you are looking at inorganic organic compounds, biological macromolecules including semi-empirical calculations, atomic charges, NMR. So, Cosmos NMR is optimized for NMR based structural elucidation, okay, remember that. In drug discovery we do not spend much time on that actually. And this is again Gromos, it is a free software, it can be used for a lot of dynamic simulations. This is called Groninger molecular simulation, a force field that comes as part of this software. It is a free software for dynamic study. It is molecular dynamics computer simulation package for the study of biomolecular systems. Okay, so, if you are using that software, you will be using this force field. Okay, more force fields. OPLS, optimized potential for liquid simulation. So, there are many OPLS, AA, OPLS UA, OPLS 2001, developed by Jorgensen at the Yale University Department of Chemistry. It is very good for liquid simulation. Okay. Then ECEPP, first force field for polypeptide molecules, developed by Momeni, Sherega and colleagues. Then QCFF-PI, this is a general force field for conjugated molecules. UFF, like I said, universal force field, they call it a general purpose force field, parameters for the full periodic table including the actinoids, developed at Colorado State University. So, they try to have parameters for all the atoms in the periodic table. Okay. Then the consistent force field. So, these are family of force field adapted to broad variety of organic compounds, force fields for polymers. Okay. So, if you are interested in polymers, metals, then maybe you can go for this type of force field. Okay. Then we also have condensed phase optimized molecular potentials for atomistic simulation studies, COMPASS, and this is developed by this particular Sun computers at Molecular Simulation Incorporated for a variety of molecules in the condensed phase, now available through Accelerase. Accelerase is a software, commercial software. So, if you are having that software, you will be having this particular also. Okay. Merck molecular force field developed by Merck company, MMFF, for a broad range of molecules. As you can see, some of these force fields are specifically developed for their internal use, which might not be available for general public, whereas things like MM2, MM3, CHARM, AMBER, CFF, you may get it as a freeware. Okay. Water plays a very important role because when you have proteins, water will be found, water molecules will be found. So, modeling water also has become a big issue nowadays. So, should I have implicit solvent, that means I have a change in the dielectric constant depending upon water or air, or should I have explicit. So, water, as you know, it is a very interesting system, it has got 3 sides. Okay. So, these and these can form the hydrogen bond donor, this can be hydrogen bond acceptors. Okay. The distance is given and the angle is given here. So, tip 3p, transferable intermolecular potential with 3 points, like 3 points, this, and tip p4p is represented by simple rigid molecule. So, the model looks like this. Okay. There is a 12 here, 6 here term. Okay. Then there is a constant Kc, this is the electrostatic constant given by this, Qi, Qj are the partial charges related to the charge of the electron, Rij is the distance between two atoms or charged sites, A and B are the Leonard-Jones potential terms. So, imagine if you have a lot of water present, the calculations increase because you need to add some extra terms. You need to consider water because water plays a very important role in hydrogen bond formation, donor as well as acceptor, ligand protein interactions, changes in the conformation, all these happens because of the water. Although the energy is as I showed you long time back is much less than 10 kilocalories, but it plays a very important role in the conformation the ligand takes with respect to the active site when it gets bound to the protein. Okay. So, water is a very important parameter we need to consider. Okay. Let us look at some functional forms of these force field. Charm, as I said, charm is a widely used force field, and as you can see this term is the bond stretching. Okay, I showed you long time back. They have a term for angle bending, they have a term for dihedral, okay. Then they have a term for electrostatic and Leonard-Jones potential. Okay. So, this is what charm used, very whatever I been talking about. Okay. So, they have very clear simple looking force field. There are files, external files, RTF, residue topology files. This stores information about atom mass, atom type, partial charges, connectivity, internal coordinates, residue definition. Then we have the parameter files, contains parameters for force constant, all these parameters. Okay. Equilibrium geometries, van der Waals, radii, other data. So, equilibrium geometry is the geometry it takes when it is the equilibrium state. Then there is another file called protein structure file, files actually used by charm force field dependent, contains information from the RTF files, okay, have a hierarchical organization of atoms, residues, meg segments. So, these are the files that are necessary if you are running a charm force field. Okay. Then comes amber. Look at this amber, amber also looks very much similar. You have the term for bond stretching, bond bending, torsion, okay, Leonard-Jones potential, the electrostatic, and of course we also have the hydrogen bond term also, that is one extra. Then CVFF, consistent valent. Okay, as you can see the bond stretching has become different, Morse term, not this type of term. Okay, they use the Morse term, and then they use the same equation for the angle bending, torsion. Okay, now you see there are a lot of cross terms there. Okay, stretch, angle, stretch, angle, like that, lot of cross terms. And then of course this is your electrostatic and this is a Leonard-Jones. Okay. So, CVFF uses many cross terms as you can see here. Okay. So, obviously you need extra parameters, these are extra parameters which you require if you are going to use cross terms. Okay. This is called CVFF force field. Another force field MMFF94, look at the equation for bond stretching. Okay. So, they have a completely different equation, they consider square terms as well as linear terms, okay, as you can see here, and you can see these are constant. Then for the angle bending also you can see square term and a linear term. Okay. Out of plane bending energy, I talked about if you have 3 atoms, sorry, if you have 4 atoms, 3 may be in one plane, the 4th one may be out of the plane. So, that is also included here. These are non-bonded interactions, okay, the electrostatic and the Leonard-Jones potential. So, MMFF uses okay, not only the quadratic term, but also the linear terms as you can see here. Okay. This is another force field called GAFF. Okay. If you look at the GAFF, so we have the stretching using the normal square term, bending, and then torsion, and then they have the standard term for electrostatic and Leonard zone. So, different types of force field terms. So, that is why in the beginning I mentioned that never mix and match force field. So, always use the same force field. So, as you can see, the functional forms can be very different between force fields, and of course, the corresponding parameters also will be very different between each force field. So, always use the same force field if you are studying a set of system and if you are trying to compare a set of system. Okay. So, we know how to use the force field, which one to select and what is the difference between this force field. Then comes the boundary conditions. So, what is this boundary conditions? If you have a molecule, I want to study the molecule. So, the molecule may be surrounded by some solvent or water, or it could be in vacuum. For example, if you are studying the energy or conformation of a molecule which is very dilute form, or if it is in a gas form, we can consider it as vacuum. Okay. So, there is no solvent interaction, there is another molecule of that same type is also not there, because if it is in gas phase, it may be very far apart. Okay. So, it has become easy, we do not have to consider a molecule non bonded interaction, or if you have a solvent, then there will be a solvent molecule interaction. Okay. So, if I have say chloroform, there will be say hundreds of chloroform surrounding my drug, then there could be lot of interactions between chloroform molecule and the drug, non bonded interaction, electrostatic, van der Waals and so on actually, or hydrogen bonds. So, when you consider vacuum, calculations are easy, we just have that molecule and study it. When you have solvent, you may surround it with water, solvent or chloroform or methanol. So, you are going to have lot of non bonded interaction between the molecule and the solvent. So, how many solvents do I consider? Layer, how many layers? So, shell. So, we can consider between R1 and R2, okay, or we can have a cutoff, that means no forces after a certain distance, because if you consider solvent up to certain 3 layers or 4 layers, then after the 4th layer it is like a vacuum, right. So, we need to balance, and of course, if you have too many layers of solvent, then the calculations also become too many. You may have almost factorial extra calculations to be done to determine all the non-bonded interaction. So, to be more realistic, you may have many layers of solvent like your molecule, and there will be solvent, or the calculations become too many, or do I make it a little bit approximate and assume only few layers of solvent. So, that is the question we need to answer. There are different approaches, some is called uniform decay. So, the interaction of this is much more than the interaction of this, So, there is a uniformly decreasing level of interactions, that is called this uniform decay. Periodic boundary condition, we will talk about this more in detail later. So, periodic boundary conditions places the molecular system in a periodic box and adds water or solvent molecules. The molecules can move in a constant density environment, basically it maintains the density of the entire system, the molecule with the solvent. So, different approaches can be followed. I can think about a vacuum, that means I have only my molecule, nothing else. So, there is no interaction with anything else. Solvent, I could consider solvent surrounding my molecule, so there could be non-bonded interaction between the solvent and the main compound or hydrogen bonds. Okay. So, how many layers of it do I consider? That becomes a challenge actually. Do I just consider 1 layer or 2 layers or 3 layers or 4 layers? So, the calculations become more intensive if I consider more and more layers. Okay. Another approach is the uniform decay of the interaction of the solvent with the main compound. Then another approach is this periodic box. This is a very important concept which is generally used when we talk about proteins. So, what it does is it places the molecular system inside a box containing water or solvent molecules. Okay. So, density is maintained constant. So, if a solvent goes out of the box, then another solvent is assumed to enter from the opposite direction, okay, that is what is called periodic box. We will talk about this little bit as we go along now. So, different types of boundary conditions needs to be considered. As you know, proteins need to be in water environment so that it can assume proper conformation, okay. For example, if protein is surrounded by water, the hydrophilic portions may come out, the non-polar or hydrophobic regions may go inside. So, the conformations can change dramatically depending upon the solvent or the boundary condition. Okay, so for example, vacuum, like I said, I may have just the molecule and I may look at the energy of this molecule. So, and what conformation this molecule takes place. So, I can study this, okay. I can calculate shape, size or heat of formation of these molecules. There is nothing else surrounding this, all alone. So, it is like a vacuum or gas phase. Or I can have a molecule or the same protein like and there is nothing surrounding this, okay. Although it is not realistic because proteins generally are surrounded by water because they are always found in aqueous medium. So, I can think of a solvent layer surrounding this main molecule. So, obviously there is going to be a lot of hydrogen bond accepting and donor happening, okay, between all these water molecules and the solvent. So, the total energy of the system can be different, the energy of this molecule itself can change, the molecule can take new conformations because of that. I can consider 2 layers of solvent. So, as you can see the amount of calculations increase, but it is more realistic, or I can consider 3 layers of solvent, okay. But then some interesting thing is the solvent at the outermost layer has interaction with the solvent in the inner layer, but outside that is a vacuum. So, these solvent face a very non-realistic forces, okay. So, there are many approaches to handle that, we will not go into that, especially the solvent in the outermost layer has this problem, okay. Whereas the main compound has no problem because you have surrounded one layer and so on, okay. Periodic boundary condition, let us look at this. What is this? When an object, so we have a periodic box, okay, and we keep the solvents. So, when the one solvent goes out from the box, we put in another solvent from the opposite direction. So, the number of solvent molecules inside the box is constant, so the density is constant. And if it is a square, then we place similar looking boxes in all sides, okay. So, we do the calculations for all. If it is a cube, then obviously you have 4 plus 2 6 sides of it. So, everywhere you assume another cube placed and you do the same calculation. So, the density of the innermost cube remains constant because if one solvent goes out during the calculation, we assume another entering from the opposite direction. So, the number of solvent molecules are constant. So, periodic boundary condition is generally preferred, which is much more accurate for considering the surroundings, okay, for considering the boundary conditions, okay. For example, this is a protein, this is a periodic box, we have assumed it here, okay, a large cube like, there are a lot of water molecules here, and so we assume similar boxes on all the 6 sides of this cube. So, we can perform molecular dynamics simulations, we can perform conformational changes. So, if one water molecule goes out from this box to the box outside, it is assumed another water molecule will enter. So, the number of water molecules inside will be always constant. So, the density is constant, okay. And why it is periodic? Because you have assumed that there are 6 more boxes of similar type on all the 6 faces of this cube. So, periodic boundary condition is generally preferred, like I said. Calculations are intensive, as you can see here. If I take a protein, I may have about 2000 or 3000 water molecules. So, we are calculating so many non-bonded interactions, hydrogen bonds with the main molecule. So, calculations are quite a lot, okay. I also mentioned reaction zone, that is another approach by which we can incorporate boundary conditions. The reaction zone, this can be considered as a replacement of atoms beyond a given distance by a thermal bath model. So, we have the reaction region, we have the stochastic dynamics here, you have fixed amount of atoms here, okay. The interaction between the bath and the dynamic region, reaction region, preserves the equilibrium structure, okay. And then this reservoir, okay, maintains the energies these solvent molecules face actually, okay. That is called the reaction zone, this is a stochastic boundary condition. Another approach is called the cutoff, okay. So, cutoffs introduce discontinuity in the potential energy and forces, okay. So, beyond a certain distance we do not assume any solvent present. So, up to that, so solvents here interact with the main compound, and this portion is assumed as a vacuum. So, obviously there is a discontinuity, okay, beyond this. So, it can create problems. So, how do they do that? There are several approaches, we will not go into that, okay. Shifted potential, that is constant term is subtracted from the potential at each value. So, different types of approaches are used so that this type of large discontinuity does not happen. Another approach which I said is uniformly decaying function, that means the solvents surround immediately has certain energy of interaction, solvents beyond that you have a uniform decay, and as you go out and out and out, the effect of the solvents on the outer layer is much less. So, you get a uniform decay rather than sudden cutoff, okay. That is sudden cutoff, which you say as soon as the cutoff here, solvents here do not contribute anything to the main compound, okay. So, we shall continue further on this molecular mechanics and force field in the next class as well. Thank you very much for your time.